Okay, so now we have valence and core electrons. And as we see here, the valence electrons, the outer electrons determine the chemical properties of the element. The outer electrons, which determine the chemical properties of an element. So these are the frontier of the elements, the electrons of the elements who are going to fight or to engage or to, we call it, determine the chemical properties. The core electrons, these are the lower one. Electrons that occupy lower energy quantum levels, the lower energy. Now, we have a fact saying the core electrons shield the valence electrons from the nucleus positive charge. So now we have a nucleus, we have electrons outside. In the middle, the valence electrons outside. In the middle will be the core electrons. These core electrons separate or shield the nucleus from the attack from the electrons, because the electrons are negative charge. The nucleus is a positive charge. How they don't combine together, attract to each other, and the atom will be destroyed. So the core electrons, they will become like a shield around, and they are exactly the shield. They are around the nucleus, preventing the outer valence electrons to attack or to attract the opposite charge of the nucleus. So if we take an example of oxygen, electron configuration of oxygen is 1s2, 2s2, 2p4. So now the core electrons are in the 1s. 1s2 are the core electrons. 6 electrons in N2, N equals 2, the main shield, the main shell 2 is, they are the valence electrons. So here, 2 and 4, 6. These are the valence electrons. The core electrons, 1s2. Valence electrons, 2s2, 2p4. Altogether would be 6 electrons. So the nucleus is positive charge. It has, for the oxygen, the monotopic oxygen, it has 8 protons. And these are out, 8 electrons out. 2 of them are the core electrons. 6, the other 6 are the valence electrons. It is important to indicate the relative energies of these electrons on the energy level diagram for oxygen and silicon. So if we see this oxygen here, so the first electronic configuration is 1s2, 2 electrons here. Next energy level will be 2s2. Third energy level will be 2p4. So as you see, we have to fill first orbital, then go to the next one, be filled. Then we come here as Pauly said, that you distribute electrons singly, then you couple. So now this electron here, the fourth, electron number 8, sitting in the, where? In the px, I think. So this one is important. Just bear in mind, this electron is the anti-clockwise motion. We come to the silicon. Silicon, 14 electrons. So we fill 1s2, 2s2, 2p6, 3s2, 3p2. And as you see, 2, 4, 6, 8, 10, 12, 14. So now we distributed the electrons singly, then doubled, coupled, and we reach to 3p2. So we put one electron here, second one here. So if you see this electron is standing, this electron for the oxygen is sitting or lower. So now they can combine together this electron with this, then to make silicon oxide. And of course, it's not simple, but it somehow will do the combination or reaction between them. So what are the four quantum numbers for both oxygen and silicon, the four quantum numbers? So as we said, the four quantum numbers go to the last, the final electron in the valence electrons, the last one. So we come to the N, and here is 2, which is the main shell, 2. Here is the, for the silicon, the main shell is 3. We come to, this is the first main principal quantum number. Now we come to the orbital. Orbital is here is P. So P will take L is 1. You remember S0, L is 1. So the P here is 1. And the P here is 1 as well. We come to the magnetic ML. So the ML, you remember, the middle one is 0. To the left, +1. To the right, -1. So here in the oxygen, the ML is -1, sitting in the px. Whereas here, the ML is sitting in the 0, in the 0 position, in the middle, which is, the middle is 0, to the right -1, to the left +1. So here is 0. Now we come to the spin. How is the spin here? The last one, the spin is -½ whereas the spin here is +½ So now you see the oxygen is taking N2, L1, Ml +1, Ms -½ Silicon is a 3, 1, 0 +½ Okay. Questions. Chromium has isotopes, chromium 50, 52, 53, 54. That's the atomic weight or mass number. The atomic number is 24, 24, 24, 24. 24 electrons. How many electrons, protons, and neutrons does each isotope possess? So now we said all of them, they are the similar electron numbers. 24, 24, 24, 20. Protons are the similar, equals to the 24. Protons will be same for all of them, 24, 24, 24, 24. Now we come to the neutrons. The neutrons here, we have to deduct 50 minus 24, it will remain 26. 26 neutron here, 28 neutrons here, 29 electrons here, and here 30 neutrons and 0 charge. Okay, so you can determine these, depend on the as we said, there is a principle, number of electrons equals always to number of protons, and the number of neutrons, they are not equals. In the monotopic, yes, they are equals, but in the isotopes, they will be higher than. So whatever you have here, 50, 50, subtracted from the 24, the remaining will be neutrons. Now, does the 3 4p atomic orbitals or suborbitals possess the same or different values of principal quantum number? Principal quantum number, they are the same, 4, 4, 4. Orbital quantum number, the same, it's a L. P is L for all of them. Now, magnetic quantum number ML is different. Maybe +1, 0, -1. And the spin, that's if we have an electron, then we have to find how does it spinning. Okay. Now, arrange these atomic orbitals in order of their relative energies. Okay. So here we have 2s, 3s, sorry, 6s, 4p, 3p, 3d, 6p, 1s. So if you arrange them, you have to use, you remember, the one, depending on the energy. The lower energy, it takes number 1, 1s2, then 2s2, 3s2. Then 4s2, there is no 4s2 here. So we have 3d. Once the 3d finish, if you remember, we can come back to the, you have to draw the, as we said, you remember this, I show you the drawing into here. The drawing here, you can see 1s2, 2s2, 2p2, 2p6, 3s2, 3p6, 4s2, then 3d. You have to memorize this, and then you can answer the questions being written there. Okay, here. So here the answer 1s2, 2s2, then 3s, 3p, 3d, 4p, 6s, 6p. Now we come to the ionization energy. The energy and electron affinity, or attraction. What does it mean, ionization energy? Ionization, the first ionization energy, symboled with IE1. Ionization energy first of a gaseous atom, of course it's for gas, is the internal energy. The delta U, the difference in the U at 0 Kelvin temperature associated with the removal of the first valence electron. So X is the gas can lose 1 electron at the first ionization energy. So it will be X plus in gas form, and there is escaping 1 electron. So when this normal, stable gas lose 1 electron, it will end up with plus charge, and 1 electron is out. So the second ionization energy, you take the second electron. So if we start with this one, and then we have the gas plus, take another electron, so it will lose another plus, will be +2. So +2 of the gas, it means lost 2 electrons. The first one with the first ionization energy, the second one with the second ionization reaction. And if you go furthermore to lose the third one, you can lose another one. So the gas will become +3, and 3 electrons are escaped from him. The high value of ionization is associated with noble gases, losing all single electrons. Okay, the high value of ionization energy associated with noble gases when losing all single electrons. The low value of ionization associated with the group 1 elements. So in the periodic table, the first group of the to the left side, you remember starting with hydrogen, the other underneath. So when you lose 1 electron, so from the first group, that's the first ionization energy because they have single electron. So the hydrogen has only 1 electron. It has no ionization energy. Bear in mind, hydrogen has only 1 electron. How can this hydrogen lose 1 electron? It cannot be, because of the only, if there is no electron, there is a disappearance of the hydrogen. And this can't happen because of the first principle law in chemistry. The matter cannot be destroyed or created from nothing. So you destroy the hydrogen if you take 1 electron from it. So that cannot happen. Noble gas, neon, argon, krypton, xenon, radon, except helium possess NS2. You remember, these possess the last orbital ending with S2 because it's filled with electrons. I don't know what is the number of N. Is it 1s, 2s, 3s? It depends on the element, atomic number. And then NP6 are stable. Removal of electron needs a great amount of energy because they are stable, because they are filled in the orbitals, so they kept potential energy very high. If you want to split electron from another in the noble gases, you need a lot of energy to destroy or separate the 2 electrons. Group 1 easily lose electron from a singly occupied, resulting X plus ion turned into a noble gas configuration. Example, if the sodium lose 1 electron, sodium with 11 electrons, losing 1 electron, the sodium property will be changed to 10. What is 10? Is argon. Okay, neon 2, argon, no, argon 18. So krypton, xenon. So losing 1 electron, it will become a noble gas. Electron affinity, so that's the attraction of the electron. The first electron affinity, EA, affinity, energy, or electron affinity of an atom is minus the internal energy at 0 Kelvin temperature associated with the gain of 1 electron by a gaseous atom. And here we have if the element is symbolized with Y, it's a gas, gaining 1 electron because it's affinite. Affinite means gaining 1 electron. So this element, the gas, will have 1 extra electron, so it will be given a negative charge. A bromine, if it's affinited with 1 electron, it will become bromine minus charge. So there is 1 extra electron added to the number of electrons with the bromine. So the delta H of electron affinity here. So here we call it not ionization energy. Here is EA, energy affinity. The delta H change of the energy will become minus 325 kilojoule per mole. If it gained 1 electron, it means there is emission of 325 kilojoule per mole. In all cases, there will be a change in the thermodynamic circle or cycle. Electronegativity. In a homonuclear diatomic molecule, electronegativity always in the homonuclear diatomic molecule, like hydrogen gas. The electron density in the region between nuclei is symmetrical. Okay, the electron density is symmetrical. Each hydrogen, we have two hydrogens, each hydrogen nucleus has the same effective nuclear charge, same effective. The disposition of electron density in the region between the two nuclei of a heteronuclear diatomic molecule like HCl may be asymmetrical. So we have here symmetrical, okay, underline symmetrical. And here we have anti-symmetrical, okay, in the HCl, because symmetrical when the homo dinuclear, when asymmetrical hetero dinuclear. The effective nuclear charge of Cl is greater than that of hydrogen. The pair of electrons in the HCl covalent bond will be drawn towards chlorine and away from hydrogen. It will be away from hydrogen. So if the hydrogen came with one proton or one electron, with another hydrogen, one electron, they will combine together to form H2. Whereas, so you see the two electrons bonded the same distance, both of them. Okay, so we see the hydrogen electron plus chlorine. It has one orbital empty and they combine together to do HCl, but the two electrons shared. Here is full sharing. Here is not sharing. It's going towards the chlorine. Why? Because the chlorine has more electronegative than hydrogen. So they still bonded to each other, but the two electrons, they are beside the chlorine or filling the atmosphere of all orbitals of chlorine. So Pauling electronegativity values of XP is a Pauling, and Lewis Pauling has founded electronegativity in 1930, defined it as the power of an atom in a molecule to attract electrons to itself. The electron withdrawing power of an atom. So here is the power of an atom in a molecule to attract electrons to itself. That's what are we saying, affinity. There is dissociation enthalpy D of the homonuclear diatomic X2 and for those of heterodiatomic XY. Periodic table shows increasing electronegativity for elements from down to up. Groups in groups and from left to right in periods. Okay, in the periods. Here in the groups or columns. Sodium 0.9 is more electronegative than potassium 0.8. Cesium CS 0.7 is the number of electronegative. Fluorine F4 is more electronegative than oxygen because they are halogen. The halogen is more electronegative than oxygen, which is 3.5, and nitrogen is a 3. Okay, so we have to know that the electronegativity increases from top to lower, from left to right. Yes, check it out. So an increasing electronegativity of elements from down to up, an increase from the lower elements to the top of, that's in the groups, from lower to upper, they increase electronegative. And from left to right, it is increased. So we have to memorize this. Now you see the electronegativity for polling values common elements from the lower to upper. If you see electronegativity for francium 0.7, 0.7, 0.8, potassium 0.8, sodium 0.9, lithium 1, hydrogen 2.1. Where we go from left to right, we can see an increase in electronegativity for lithium 1, beryllium 1.5. You go to boron 2, carbon 2.5, and so on till fluorine will be 4. Okay, look. Size of ion. So we need to know the size of an ion or ion. The process of ionization results in contraction of the species owing of increase in the effective nuclear charge. Similarly, when an atom gains an electron, the imbalance between the number of electrons causes the anion to be larger than the original atom. So if you see here, sodium gas lost 1 electron, leaving it with plus charge. Fluorine get this electron and become negative charge. It means extra electron with the fluorine. And you see here ionic radius or radii. Values of ionic radii are ion. This is the radii or radius between ions, may be derived from the X-ray diffraction data, but experiment data gives internuclear distance, and this will be taken to the sum of ionic radii of cation and anion. Internuclear distance between cation and closest anion in the lattice is R plus R. So we combine them together, the radii of the anion plus the radii of cations. Lithium with halide form lithium halide, as lithium plus means lost 1 electron cation, so it become cation. And the halogen minus, which is gained this electron from the lithium, it's become an ion, forming lithium plus halogen minus in the lattice as the internuclear 2 radii distances, which is lithium X. So we can see here the halide gain 1 electron from the lithium. Lithium lost 1 electron, became cation. The name is cation, came from losing 1 electron or losing 1 or more. An ion is gained 1 electron, have extra 1 electron or more in the outer shell. But they will form a structure, a crystal or something, and there is a distance between the 2 R's of the XX. This is measured using X-ray diffraction data. So the distance between them, we have to consider the radii of the lithium cation plus the radii of the halogen or halide anion. So it's been measured, and there is values for each of them. So cation, lithium, sodium, potassium, the R plus of the lithium 76, sodium 102, potassium 138. But the anions values, which is R minus, is for the fluorine 133, chlorine 181, bromine 196, and iodine anion is 220. Okay, so we come to the boron electron configuration 1s2, 2s2, 2p1. So that is one electron in the last shell of p suborbital. The 4 quantum number belong to 2p1. So what are they? The number 2 is the main principal quantum number. P is the L, which is not 0 but 1. And the one electron sitting in the ML plus 1, and the spin is standing plus half. Questions you have here, you can practice and find out how are they solved. And we talked about valence and core electrons before, you remember. And then now I stop here.